All right, today we'll use Newton's second law to explore rotational motion. Remember that our set of analogies that we've had, that for instance in kinematics, we could replace every x with a theta, every v with an omega, and every a with an alpha. And then in dynamics, we could replace every f with a tau, and every m with an I, which is really iota, but I. And so this sort of implies that we should be able to take Newton's second law, which is F net equals ma, and generate a rotational equivalent to it by making those substitutions, and in fact that's true. The second law in rotational form is tau net is I alpha. Again, it's just coming from replacing, by analogy, F net equals ma. We'll get some practice using Newton's second law to analyze rotation around a fixed axis, that is, one which is not allowed to move or itself rotate. At the level of this class, we do not allow the axis to rotate ever. It introduces a lot of complications mathematically, and while it does lead to some interesting physics, the output is probably not worth the input of work we'd have to do. So we'll let only the axis not be able to rotate. We will later allow it to move. Right now we're not going to allow it to move either. But later we'll allow it to be able to slide sideways as long as the axis of rotation itself does not bend. So consider this force. A bar is attached to a wall via an ideal pivot. Find the force in newtons that must be applied vertically at the far end in order to keep the bar horizontal. As usual, after reading a physics problem, the best thing to do is to draw a picture. In this case, almost certainly a free body diagram because of the fact that we want to get a force. And unlike the College Board, which recommends all of the free body diagrams be drawn around a little black dot, they like to do this. And they say, draw your free body diagram this way, where we would say, oh, well, we have the weight pulling downward, and we're pulling it upward. But also, there's the hinge itself is also pulling upward. And so this is what we would call a College Board free body diagram. And if you're taking the AP exam, you should do what the College Board expects you to do so you get better credit. But in this particular case, I think they're just flat out wrong. This is not as helpful as a little cartoon version because this doesn't tell you where those forces act, so it will not allow you to cause any kind of spin. I think they push this for the case where they're talking about particle motion, things can't spin, and they don't want people thinking that they can by offsetting and so on. But now that things can, at least in principle, rotate, we should put the forces where they act. So here we have the bar. Gravity acts at the center of gravity. That's what the center of gravity is. So the entire mass of the bar produces an Fg that acts as if it were all concentrated here. The pulling force is given as being here on the right end, and as said before, the board or bar is in contact with a hinge or a pivot that allows it to spin. I'm going to call it a hinge so that I don't have to reuse P, which I've already used for pivot. So F sub H for the hinge, and I'm going to say that that might also be holding up the bar, and later we'll see that it is. Once we've done that, we compute the torque about the hinge, and then set that torque to 0. Why do we pick about the hinge? Well, kind of duh. It's where the thing's going to spin if it were to spin. So it's a natural place to say, let's compute torques and rotations about that point. It turns out that because the bar doesn't actually accelerate in any angular sense, we could actually pick anywhere we want and the problem would be equally solvable. But it probably makes the most sense if there's a natural place to put the rotation point, put it there. If there's an axis or a hinge or a pivot, then that's where it's going to rotate if it can, so it will be simplest to compute around that point. All right, so we want to get the torque around that point, which would be the torque from the hinge plus the torque from gravity plus the torque from the pulling force. But the the linear line of action of the hinge goes through the axis. And so the moment arm is 0, which means that there's no torque exerted there either. On the other hand, gravity has a line of action that is this, which means it has a moment arm, which is this, which we'd call L over 2 if the bar is length L. And the pivot force has a line of action like that, so its moment arm is clearly this whole distance, which is L. So we get Fg times L over 2, and Fp times L. Secondly, if we look at the sense of these rotations, the gravitational torque is going to try and spin this thing clockwise, which we know comes in as a minus sign in our usual convention. Whereas the pivot force is going to try and rotate the bar counterclockwise, so it comes in with the plus sign. So all told, we get that the net torque is Fp times L minus Fg times a half L. But we want that torque to be 0 because we don't want it to rotate. So we set that whole expression to 0, and we can solve for the important result, which is that the pivot force has to be 1/2 the gravitational force. As sort of a quick aside, if we went with Newton's second law again, F net equals ma, then we would have Fh minus Fg plus Fp is 0, because there's no acceleration linearly either. So Fh is the difference of Fg and Fp, and we see that Fh is also 1/2 mg, that the hinge force has to pick up the other half of the weight, which makes sense. If the thing isn't going to fall, then the weight needs to be counteracted by whatever upward forces we have, and they share equally because the center of gravity is at the center of the bar. If the center of gravity were somewhere else, then they would still sum to the weight, but they wouldn't share equally. Okay, the bar is released. Find its initial angular acceleration in radians per second squared. Keep in mind that the rotational inertia of a bar about its endpoint is 1/3 ml squared. Well, if we redraw our free body diagram, which I should have but didn't, would have an Fg here. We would have some other hinge force there. But now tau net would only be Fg times L over 2. You'll notice that here I haven't used the minus sign, and maybe that's bad, to be consistent, that we still have that this goes this way. And for this problem, I'm going to take this as positive theta in the clockwise direction. Why? Because the acceleration's in that direction, and in general, it helps to have one of your axes line up with your acceleration. If we didn't do that, then we would have had tau net equals minus Fg times L over 2. But down here, we'd also have its bi times, it had to have a minus alpha to indicate the direction. And we can see the minus signs would cancel. So I'm going to stick with my original one. And I'm going to say a half mgl is 1/3 ml squared over 2. So we can solve that for an interesting result, that the angular acceleration is 3/2 g over L. Is this always true? I've had students ask. It's always true for a bar which is let go when supported around one end. In other words, in this problem, it's always true. But this is not a generic thing, the same way that you can say like things that free fall accelerate with g. You can't say that anything that's spinning has an acceleration of 3/2 g over L. All right? It's very specific to the particular setup that we have here. If you grind out the numbers, which are really the least interesting part, you find that it's 11.3 radians per second square, which is an acceptable but not particularly huge acceleration. All right, just like before, let's apply the linear version of Newton's second to this system, specifically to the vertical motion. That is that F net y equals ma_y. But the ay of what? When all we dealt with was point particles, that question had no meaning. Of course, the acceleration was just the acceleration. But now every point of the rod has a different linear acceleration, which you can see pretty easily because if this is the rod and it rotates down a little bit, that this point hasn't accelerated at all, whereas this point has undergone considerable acceleration. So they have different accelerations. So we have to now talk about, in this, what A do we have? And it turns out that we use the center of mass, which is also known as the center of gravity. Not only does the weight act at the center of mass, the center of mass will also undergo acceleration as if all of the mass were concentrated there and all the forces acted there. It stands in for the extended object in our analysis. Like every other point on the bar, the center of mass will be tracking out a circle, in this case with radius 1/2 L. We know how the tangential acceleration and the angular accelerations are related. That is that A tangent equals R alpha. We get that, as a quick reminder, by the way we defined our angles is we had arc length S with radius R, and we said that theta was just S over R. So S equals R theta. So delta S over delta T is R delta theta over delta T, because r doesn't change, but s over delta t is just the velocity. And delta theta over delta t is just the angular velocity. And then we go here and we say, well, delta v over delta t will be r times delta omega over delta t. But omega over delta t is just alpha, and delta v over delta t is the tangential acceleration. So then we're back to this, which is what we want in the first place. All right, if we wind that through, then our acceleration ay will be the radius L over 2 times the acceleration we just found, which is 3/2 g over L. The L's, of course, cancel. The 2's will multiply together, and we'll get the acceleration of the center of mass is 3/4 g. All right, it's not quite in free fall because, of course, it's not actually falling. It's being held up a little bit by the hinge. Let's figure out how much. So here's our free body diagram with the acceleration and center of mass indicated here. It's not a force, that's why it's a little dashed thing. So we have F net y equals MAY, or FG minus FH equals MAY. FH is mg minus m times 3/4 g. FH ends up being 1/4 mg. Remember, when the bar was supported at both ends, the hinge had to provide 1/2 of the weight, but now it only needs to provide 1/4 of the weight because it's okay that the center falls a little bit. All right, this tightly wound tube of paper masses 1.6 kilograms and has a radius of 7 centimeters. It's free to rotate around its axis but cannot move. When a force Fp is applied as shown, the tube has an angular acceleration of alpha is 3 radians per second square. Find Fp in newtons. Here we assume the amount of paper that comes off the tube is negligible and that the tube extends all the way to the center, so we can model it as a solid disk, and the moment of inertia of a solid disk would be 1/2 mr squared. Again, let's do free body diagram. Here we have, of course, we're pulling down. We were given that. We also know that gravity is going to pull down at the center. And there must be something keeping this from falling, which I'm going to call an axle, and give the name FA. And we're given that this causes a rotation whose angular acceleration is alpha and is known. So we end up just saying tau net equals I alpha. Tau net is going to be Fp times, well, what is this moment arm? That's the line of action. This is the moment arm. Fp is perpendicular because it's tangential. So this thing is perpendicular to tangent. It must be the radius. So Fp times r. And you'll find a lot of times circular objects like this are very convenient because the forces tend to be tangential, so the moment arm tends to be the radius. Not a guarantee always case, but worth checking and worth being comforted by when you see it. And then we're going to add in the torque due to gravity, but that's 0 because gravity acts at the center. And the torque due to the axle, but that's also 0 because it also acts at the center of rotation. And this has to be I alpha. In fact, we were given what I is, so I'm going to put that in, 1/2 mr squared alpha. So Fp ends up being mr alpha over 2. When you grind out those numbers, it's 0.168 newtons. Constraints due to ropes and pulleys. If the pulley turns without the rope slipping on it, then the rope speed must exactly match the rim of the pulley. Right? That's what we mean to not slip. Right? If the speed were different, then it would slide along the pulley either forward or back, and we would say that the rope was in fact skidding or sliding. The attached object has to have the same speed and acceleration of the rope. At the rim, the linear speed is omega r, so the object, whatever it is attached to the rope, has to have that velocity. Why there? Because if the object that was attached to the rope had a velocity that was different than the rope, then the rope would either stretch or bunch up, and we're not letting that happen. So we get this connection once again that a velocity is omega r. We'll see that a lot, and it always comes back to the fact that while something's spinning, points on the rim have a linear velocity, which is omega r. Likewise, the acceleration of that object has to be alpha r. That gives us some constraints that we can use to solve some equations. For instance, a winch consists of a rope wrapped around a 3 kilogram cylinder of radius 4 centimeters. The cylinder is free to rotate about its axis. Attached to the other end of the rope is a bucket whose mass is 2.5 kilograms. Treat the winch as a solid cylinder with a rotational inertia of 1/2 mr squared. Find the acceleration in meters per second of the bucket when released from rest. All right, after reading the question, often the best thing to do is draw a picture, and when forces are involved, very usually a free body diagram. So let's look at our free body diagrams. We have for the bucket, gravity is pulling downward, and there's a tension holding it or pulling it upward, and there's some acceleration of the center downward. This can be treated like a point mass. The bucket is not allowed to spin or rotate, so it's basically like something from earlier in the class. On the other hand, the winch, and again, I don't really like how they say draw it as dots, but the winch has a weight pulling down, Fg star, because this weight is not equal to that weight because their masses are not the same. Close, but not the same. And the tension is pulling down, and it acts as if it's pulling on the point where it's leaving the cylinder and pulls it downward. And then there must be something, an axle or something holding it up. This induces a counterclockwise rotation, so that alpha. Then we set up Newton's second law. Second law for the bucket says that gravity minus the tension is ma. Again, I've taken downward here to be positive because the acceleration is already known to be downward. And then I'll be consistent with that, it won't matter, that Fg star plus Ft minus F axle is 0. And then these are the linear versions. The rotational version is that tau net equals I alpha, but the only torque is coming from Ft, so Ft times R equals I alpha. Note that the force of the axle is unknown, but in D is whatever it needs to be to make the thing not fall, but it doesn't contribute because it's unconstrained, and it doesn't matter because the winch doesn't accelerate linearly, and the axle exerts no torque. Also note, if we highlight the things that we know in this problem, well, we know Fg, more or less, because we know this, and we know Fg star, because we know this, and we know, of course, the mass, and we know the radius. What do we not know? Well, we don't know either of the accelerations. We don't know Ft, and we don't know F axle. And I have, therefore, 4 unknowns. 1, 2, 3. 1, 2, 3, 4. And I have only 3 equations. So we feel like we're in a little bit of trouble here. We don't have enough to get everything we would need. But of course, this problem is not really insolvable. There should be a solution because if we did this, we'd expect 1 speed to come out. How do we resolve that? Well, we remember that there's a connection between how fast the bucket descends and how fast the winch rotates. The bucket must have the same acceleration as the rope. And the rope must have the same acceleration as the winch's edge or rim. That is to say, A must be R times alpha. So now we can go back and go into our equations. If we solve Newton's second for the bucket, we'll find that the tension has to be Fg minus ma. So we can put that in here. And then we just do a lot of algebra. We say we divide by R, which we can do. And then we say that alpha is also A over R. So we get this equation. And then we just do a bunch of solving, and we find that the actual acceleration ends up being the mass of the bucket over the mass of the bucket plus 1/2 the mass of the winch, all times g. When you actually substitute numbers, you get 6.13 meters per second squared. It's about 2/3 free fall, but not quite free fall. The AP people might then say, instead of solving this problem, they say, consider this problem, get the acceleration, or think about the acceleration, and then replace the cylinder with a hoop of the same mass. What would happen to the acceleration? And you could grind this out and get the number and compare it to this. Or you could stop and think and say, well, wait, if I make all of the mass at the radius rather than being distributed throughout the cylinder, that makes the hoop harder to spin than the cylinder was. So the effect of the tension is less, so we'll get less acceleration. So we should get less acceleration, and we do.